Hello, Astronomy. Mr. Janowski here. So this is the second part of the slides for chapters 14 and 15, stellar evolution and stellar remnants. So in the first part, we kind of previewed everything, and we mostly talked about low mass stars. And in this part, we're going to talk about the high mass stars and how they live and die and what they leave behind. And you'll see why there's a big distinction. We make a big distinction between the low mass and the high mass stars. So let's get started with that. So to review from last time, what lives longer, low mass stars or high mass stars? It is actually the low mass stars that live longer. So even though they have less fuel than the high mass stars because they have less mass, they go through their fuel at a much slower rate. High mass stars have more fuel, but they go through it much more quickly. So which of the four fundamental forces drives stellar evolution? Remember, the four fundamental forces are the strong and weak nuclear forces, electromagnetism, and gravity. And the one that drives stellar evolution is gravity. So gravity builds all the big things in the universe, and it governs the lives and deaths of stars. So what will the sun spend most of its life as? So remember, we define a star as being alive as when it's fusing elements in its core. The sun will spend most of its life as a main sequence star. So a star is on the main sequence when it's fusing hydrogen into helium in its core. And that will be the largest part of the sun's life. The sun will spend about 10 billion years there while it's alive, and far less time in any of the other stages, or even all of the other stages combined. And what kind of corpse will the sun leave behind? So once it stops fusing elements, it will be a dead star, and the kind of dead star it will be is a white dwarf. So low mass stars like the sun end up as white dwarfs. So we talked about the whole life story of the low mass stars last time. Now we're going to do the life story of the high mass stars. And they have a very different life story. They're going to go through very different stages. So the dividing line between a low mass star and a high mass star is about 8 times the mass of the sun. So if you are less than 8 times the mass of the sun, we're going to consider you a low mass star, and you're going to live and die a certain way. If you are more than 8 times the mass of the sun, then your life story is going to be different. And you're going to end up in one of 2 different possible ultimate fates. So if we're talking about the high mass stars, it all starts out kind of the same. So it's going to start off as a giant, interstellar gas cloud. The gas cloud is going to have more stuff in it. So the fact that there's more stuff means there's more mass, so gravity is going to work better because there's more mass for everything to pull on. So it's not going to be a gas cloud for quite as long. So for a low mass star, maybe 20 million years. For a high mass star, maybe 10 million years. And then it'll be a protostar. So it'll all collapse down to something like this, and it keeps bringing more and more mass into it. And the center of this cloud starts to get more and more dense. That's the protostar stage. And that'll last, about 1 million years. About as long as the protostar in a low mass star. And then eventually, just like with the low mass stars, the core is going to get hot enough for fusion to occur. So it's going to start fusing hydrogen into helium in its core, and that's going to create the outward pressure that stops the collapse. So it's not going to keep collecting more and more stuff after this point, because before this point, gravity was bringing more and more things together, and there wasn't a whole lot stopping it. There was a little bit of heat. There was heat, but not nearly as much heat as once fusion starts. So once fusion starts, outward pressure stops more things from collapsing. So remember, now we're doing the high mass stars. So because this star is more massive and there's more stuff pulling on all of the other stuff, gravity's going to squeeze this all together more. So it's going to squeeze it into a hotter and denser star. And the fact that it's hotter, remember Wien's law, is going to make it bluer. And if you remember the Stefan-Boltzmann law, the fact that it's hotter and bigger is going to make it much more luminous. Much luminous, not luminance, luminous. It'll be much more luminous. So bigger, bluer, and more luminous, brighter. So remember, we had this at the end of the last chapter. This is the mass-luminosity relationship. So for a main sequence star, there's this approximate relationship where the luminosity is proportional to the mass of the star cubed. So if you were the sun, you have 1 times the mass of the sun. Well, 1 cubed is 1. So you would have 1 times the luminosity of the sun. However, if we're talking about a star that's right on the border between low mass and high mass, a star that has 8 times the mass of the sun, 8 cubed is 512. So that kind of star is going to be 512 times as luminous as the sun. So now you get to see why the high mass stars don't live as long. So that star has 8 times as much fuel, but it's going to be using it at 512 times the rate. So it's going to go through all that stuff way, way quicker. So it turns out that the high mass stars don't live as long as low mass stars. And in fact, they don't live nearly as long as the low mass stars. So a star like the sun is going to spend 10 billion years, so 10,000 million years on the main sequence. A high mass star might spend a tenth of a billion years, so only 100 million years as compared to 10,000 million years. And if it's more massive than that, it could spend even far less time there. So yeah, maybe 100 million years, maybe 10 million years. So they don't live nearly as long. So the story starts to get a little bit different at this point, because remember, the low mass star goes from main sequence to red giant to yellow giant back to red giant. High mass stars don't do it. So the high mass star is going to go from main sequence right to a yellow giant, and then it will quickly go on to the red giant stage. So not red, yellow, red. This will just go from main sequence straight to yellow and then to red. So for a low mass star, it might spend 150 million years in this yellow giant and second red giant stage. So how long is the high mass star going to be a yellow giant and red giant? For far less time, only about 1 million years. So we spend 150. We will. The sun eventually, when it gets to this point, we'll spend 150 times as long in these two stages as a high mass star does. So while it is all right, a main sequence star. Let me start here. A main sequence star is a star that fuses hydrogen into helium in its core. And after it stops doing that and starts fusing other things, it starts fusing the helium into other things, carbon and other things like that. It leaves the main sequence and it becomes some type of giant star. So the way this works is the star has to be very hot to fuse hydrogen into helium, and it has to be even hotter to fuse helium into other things. And it has to be even hotter than that to fuse, the next things into the next things. So what's going to happen is, as the star progresses, it keeps switching from one type of fuel to the other. And it keeps going up and up and up. So it does this up until it gets to iron. Iron, atomic number 26, is hugely important in this story. Here's the reason why. So think of the sun, which is a main sequence star. So the sun is fusing hydrogen into helium. It takes a lot of energy to fuse hydrogen into helium, but then E equals mc squared happens, and you get more energy out. So the fact that you're getting more energy out than you're putting in is what's providing the heat that's causing the pressure that's supporting, the core of the sun against gravity. And it keeps working like that. So once it fuses helium into other things, takes a lot of energy to do that, but you keep getting more energy out, and so forth, up until you get to iron. Iron, atomic element 26. So I'm sorry, this is too small for me to see. I'm not going to count it out. But whatever 26 is, somewhere in here, that might be it. I think that's 26. When you try to fuse iron, it takes a lot of energy to fuse two iron nuclei together, and you get less energy out. So that's a big problem. So instead of undergoing this fusion and getting enough extra energy to support the star against gravity, you've lost energy in this deal. So iron is a big problem for this. So you're not getting as much energy out, which means you're losing that outwards pressure from nuclear fusion, which means gravity is going to win, and it's going to win really, really fast. This is one of the neat things. There's a video I'm going to link to for this, where he goes over all these different stages. But these different stages in a star, they last for millions of years. And then the later stages, when it starts switching from fuel to fuel, they might last for only thousands of years. and then one of the stages lasts for only a day. And then finally, once the star starts to fuse things into iron and tries to start fusing iron, it loses, and it happens in less than a second. So it's just neat the way these timescales work. They're huge, way longer than any human can reasonably comprehend. And then once it gets to this stage, everything happens in less than a second, which I love that. So all of a sudden, the star is trying to fuse iron. It's losing energy every time it does so. And all of a sudden, gravity wins. So all of the outer layers of the star are going to come crashing down onto the core, and they're going to basically bounce off of the core and blow up out into space. And a huge amount of energy is going to be released in the form of neutrinos and other things. And this is what a supernova is. So all of this stuff is going to get blown out into space. So this is when the elements that are more massive than higher atomic numbers than iron get fused. So, I mean, I love this fact too. So if you think, humans are 70% or 75% water, which is H2O. So some of that H has been around literally since the Big Bang, so 13.8 billion years. But you've got other things in you as well. We're carbon-based life forms. So we have a lot of atomic element number 6, carbon, in us. Where did that carbon come from? Well, that carbon wasn't created in the Big Bang. That carbon was created in stars. So while stars were going through their life and fusing small things into bigger things, at certain points, they made carbon. And they kept making the other things up and up and up. So, for example, calcium is atomic element number 20. So the calcium in your teeth and the calcium in your bones, that was once inside the core of a star. The star made that calcium while it was alive. And so forth until you get to iron. So there's iron in your blood. The iron that is in your blood at one point was in the core of a star, and that iron basically murdered that star. That iron is what killed that star. And you keep going up and up and up. So this is the story. This is called stellar nucleosynthesis, how the nuclei of atoms are made in stars. And stellar nucleosynthesis works up to about 26. So it's here. And then, of course, you notice the periodic table doesn't stop here. It goes on and on and on. So where did the other stuff come from? The other stuff, at least the majority of the other stuff, was formed in the instant that the star died. So when you have this supernova and all this tremendous amount of energy is being released, this is when it's hot enough to start fusing iron into other things and getting more things. So everything after 26, that's when all this stuff gets created. So you have trace amounts of, gold and heavier things like selenium and other things, in your body. And perhaps you have gold or silver jewelry. Well, those things are higher on the atomic, they're later on the periodic table than iron is. So that gold that's in your jewelry, if you're wearing, a gold ring or a gold necklace or gold earrings or whatever, that gold, where did it come from? Before we dug it out of the ground, billions of years ago, that gold was created in the violent death of a massive star. That's where all of the big things come from. So back to the story of the evolution of stars. There's going to be basically two possible fates depending on the mass of the star. So the lower mass, high mass stars, meaning the star when it was alive had a mass of between 8 to about 20 times the mass of the sun, they will die a certain way and they will collapse a certain way, and we'll go into great detail on this in later slides. The lower mass, high mass stars will become neutron stars. If the star was more massive than that, so if the star was about 20 times the mass of the sun or greater while it was alive, when that star collapses, it will form a black hole. So yeah, later in this chapter, we'll get into the black holes in some detail. So here again are all the stages for the high mass stars. And I love the way this works. In millions of years this time, it's a gas cloud for about 10 million years. It's a protostar for about 1 million years. So this star, this particular one we're talking about, must have been fairly massive because it was only on the main sequence for about 6.5 million years. remember, the sun is going to be on the main sequence for about 10,000 million years, and this star only 6.5. And then it goes through its different stages. In the video, he talks about how long each of these stages, each of the parts of these stages last in some detail. And then finally, at the moment of its death, when it starts to try to fuse iron, it only lasts for, that stage lasts for less than a second. And then this very massive star is going to end up being a black hole. And how long will that live? An absurd amount of time, but more on that in later slides. So here is, it looks a little funny, but this is actually an HR diagram for a high mass star and the different stages that it goes through. And this is comparing them. So again, the big thing to me is a star like the sun will be a main sequence star for about 10,000 million years. A very high mass star, one big enough to become a black hole, won't spend 10,000 million years on the main sequence. It'll spend about 6.5 million years. And then the other things go on and on. So neat stuff. So if we're comparing these things, notice that both kinds of stars, low mass and high mass stars, start out their lives as interstellar gas clouds. And depending on how big that cloud is, it's going to collapse into either a low mass or a high mass star. And then it goes through the whole thing. And then if you're a low mass star, you don't end up in an explosion. Low mass stars don't go through supernovas. So the sun is not ever going to explode. Stars like the sun will eventually just kind of fizzle out, and the core will remain there, and the outer layers will drift away and join a gas cloud. If you're a high mass star, different lifetime, it goes through all this stuff much quicker, and then you will have a violent supernova explosion, and all of your stuff drifts away, and again becomes a gas cloud. And again, this is the very poetic part of this stuff, is that gas cloud, well, what's going to happen to that? It might collide with another gas cloud and eventually start collapsing again, and the whole thing starts over. So circle of life going on here. And again, this class is astronomy, but this is one of the very big things that astronomy answers. Where did all the stuff come from? So it all started with the Big Bang, and that gave us hydrogen and helium and a little bit of lithium. But where did all the other stuff come from? If you look at the periodic table of the elements, where did elements 4 up through 100 the last ones are artificially made. Don't worry about those. Where did all the other stuff come from? Where did the carbon, that's making up my cells, where did that come from? Where did the calcium in my bones and my teeth? Where did the iron in my blood come from? Where did, the gold in my necklace, where did it come from? It came from stars. It was either created while the star was alive, if you were talking about things up to iron, element number 26, or if it's an element beyond that, it was created in the death of a star. And it goes on and on and on. Now, let me quickly mention one more thing. So, stellar nucleosynthesis. This is how stars create all the elements up to number 26, iron. Iron is huge. This is the swing point in the whole story. Elements beyond 26, those can be created through supernova nucleosynthesis. So all those get created really just at the death of the star. So that's kind of orthodox astronomy. There's kind of a newer idea that says, well, those heavier elements can also be created another way, which is through the collision of neutron stars. So we'll talk about neutron stars later in this chapter. But this is where all the big stuff comes from. And like Carl Sagan said, we're star stuff. And we literally are. This is how all of the things you're made of got created in the lives and deaths of stars. So astronomy, it's a luxury science, but it does answer these huge, huge questions. So I love this stuff. So here's, the crash course on the lives and deaths of high mass stars. So link to that in the description. So to review, what is the dividing line between high and low mass stars? The dividing line is, there should be apostrophes there. No, not apostrophes, dashes. High and low dash mass stars. It's a hyphenate. The dividing line is about 8 times the mass of the sun. So according to our models, 8 times the mass of the sun is where the differences start to happen. So if you're 8 times or less, you'll be a low mass star, you'll live your life, and you will eventually become a planetary nebula and just kind of drift away. If you're a higher mass star, higher than 8 solar masses, you're going to die differently. You're going to die in a supernova. So which type of stars live longer, the high mass or the low mass stars? It's the low mass stars that live longer. And again, you can see why, because we have this luminosity mass or mass luminosity relationship for the main sequence stars, and the luminosity of the star, so how much light it's putting out, which is how quickly it's going through its fuel, is proportional to the mass of the star cubed. So again, if you're right on the border, if you're 8 times the mass of the sun, well, you've got 8 times as much fuel, but you're going to go through that fuel 8 cubed, which is 512 times quicker. So that's why the high mass stars don't live as long. Even though they've got more fuel, they go through it much quicker. So what kind of corpses do low mass stars leave behind? Again, a star is considered alive while it's undergoing nuclear fusion. And then after it stops doing that, we consider it a dead star. And low mass stars, 8 solar masses or less, will end up being white dwarfs. So there's the life story of a low mass star. And how about the high mass stars? So 8 times the mass of the sun or more. They will end up either as a neutron star, if it is a lower mass, high mass star, so about 8 solar masses up to 20 solar masses, it will end up being a neutron star. And if it were a high mass star, so 20 solar masses or more, it will end up being a black hole. And more on that in the later chapters, or not the later chapters, the later parts of the slides. So that's it. Watch the crash course video on the lives of high mass stars. It's very interesting. And, hopefully you're finding this stuff interesting.